Good morning, good afternoon, and good evening. I'm your host, Aya Takasen, and I am here with our presenters, Simon Bates and Tom Concolino. Tim is out this week, so Tom is stepping in, and he will be moderating the Q&A session today. Thank you for joining our webinar series, Beneath the Surface Pair Distribution Function, or PDF analysis for everyday battery analysis. In this webinar series, we will discuss how to leverage X-ray analysis techniques to gain insights into battery performance. Our expert speakers will share the best practices and real-world applications. But before we start, a few housekeeping items. This is going to be an interactive session, and I will be posting relevant links in the chat window. And we will be taking your questions live during the webcast and answering them during the session, so please don't wait until the end to ask. Please submit those questions via the Q&A button at the bottom of your screen. We will not be monitoring the raise the hand function. We will try to answer as many questions as we can during the live session, but we will respond to any unanswered questions directly after the session is complete. If for whatever reason you have a difficulty viewing the webinar, please note that it is being recorded and you'll be able to view the recording beginning tomorrow. Okay, with that said, I will turn it over to Simon and Tom.
Greetings everyone. Thank you for attending this webinar. This is the third one in the series of battery specialized webinars in X-ray diffraction, X-ray analysis. And today we will be discussing pair distribution function, that's PDF analysis for everyday battery analysis. So in this webinar, we will discuss some cathode materials for lithium-ion batteries. In fact, we'll be discussing them at the atomistic level. And in particular, we'll be looking at total diffraction and pairwise distribution functions versus traditional Bragg methods or crystallography methods, and how they can both help us understand the structure of batteries at the atomistic level and how they change through cycling and also how they change through composition. And we'll look at the application of small box and large box models, and you'll understand a little bit more about small box and large box models by the time we finish, and how we can apply that to characterizing PDF data, and again, to get more detailed atomistic information about what's going on inside a cathode material. So why is this topic important? Well, as I travel around to various battery companies globally, a common theme that emerges is that there's a big issue with cathode material. It's one of the many reasons for battery failure, for lack of longevity. You get aging and degradation of the cathode materials. And it turns out that total diffraction and pairwise distribution function analysis can give you a really detailed atomistic level model of what's going on inside your battery during these charge and discharge cycling, what's causing the aging, what might be causing some of the problems. And it allows us to fine-tune the composition, exactly what cathode material should you be designing, how to design that material, how do you modify the composition, 811, 523, et cetera, how to deal with doping issues. Maybe doping is something that could be really important in improving the longevity of and optimizing cathode design. Now, it's not only applicable to cathode material. The same type of analysis can be used for solid anodes and can also be used for solid electrolytes as well. So as we go through this, I'll be talking specifically about cathode material and more specifically about NMC type material, but it can be pretty much globally applied to any sort of cathode, anode, and solid electrolyte. So having said that, let's start off with an analog to help us get our feet on the ground and start thinking about the simplest model of NMC type cathodes. So this particular material, if you view it from traditional crystallography, it's a trigonal structure. It's R3 bar M or R bar 3M, depending how you like to read that. It's essentially an hexagonal structure. And we have lattice parameters that define that structure. But for me, the most important or characteristic features are, number one, we have these cobalt layers, these metallic layers, and in NMC, of course, that would be the nickel manganese cobalt layers. And these have an hexagonal, like honeycomb symmetry, and they form two-dimensional sheets that give the rigid structure to the battery itself. So in these plots I'll show you of the atomistic level, cobalt is the darker color one, this darker purple or darker blue color. And then surrounding the cobalt, we have oxygen on both sides. So the cobalt is coated with oxygen on both sides. That's the red color or the intermediate color. And then lithium in the middle, in the channel, this is the lighter color in the plots. And all the atomistic models will have this same color or grayscale density. Now, once we have the atomistic structure, we can do a lot of predictive analysis with this. And one that's very useful is called bond valence calculations. Given us the valence state, so cobalt 3 plus, lithium 1 plus, oxygen 2 minus, then we can construct this bond valence model. And what I'm showing here inside the lattice is the mobility or the degrees of freedom that lithium has within this structure. So although it has, preferred positions, I mean, it's a crystal structure after all, and the framework of the cobalt on the top sort of gives lithium predefined positions where it likes to be, it's actually free to move up and down this channel. And this is the critical design parameter of this type of NMC material, is that the lithium is free to move up and down the channels. That's what actually makes it an effective cathode material. And as my colleagues have pointed out, the width of this channel, the opening in the channel is absolutely critical to how the battery material can function itself. So let's have a look at this crystallographic model in more detail. What actually is within that model that allows us to do these predictive calculations? And is it enough? Well, at the crystallography level, we have to consider the asymmetric unit cell. All the degrees of freedom of a crystal structure are tied up in its asymmetric unit cell. Everything else outside the asymmetric unit cell is defined by symmetry operators of one type or another. And it turns out for lithium cobalt 3 oxide or NMC type structures that we only have 3 atomic positions that are free and open for definition in this structure. That's all. So a crystal of billions of atoms in this sort of crystallographic model is defined by 3 average atoms. And it turns out the position of lithium and cobalt is completely fixed in this model. They're fixed by symmetry. So although we know this is, it's a battery material, and we know from BVS calculations the lithium moves around quite a bit inside the channels, according to crystallography, the lithium cannot move. It's bound at a special symmetry site. So that tells us straight away that traditional crystallography, Bragg models, are idealistic and overly constrained in terms of helping us understand what's going on inside a real battery cathode material. In trying to characterize and understand lithium mobility in real materials, this simplistic Bragg-based crystallography model is not going to help us. We need to go a little bit further. Now, we can introduce some disorder parameters into this model to try and help us understand what might be going on. And we'll look at these in more detail as we go through in the PDF. But one of them is called occupation numbers. So that's essentially how much lithium or how much cobalt on average is present at these sites. So you can imagine if lithium is leaving through the layers, then the lithium occupation will drop down. And also thermal parameters, which gives us some idea of the uncertainty of atomic positions. But nevertheless, they are overly constrained by symmetry and not that useful for us. So we need to have something with a bit more punch to it, a bit more robust modeling what's going on at that detailed level inside a material. And that turns out to be the PDF, or pairwise distribution function. And what it looks at are atom-atom pair relationships. So to give you an example of that, if I center on this cobalt atom, and I look at all the surrounding atoms around it, these are atom-atom pair relationships. Now, PDF theory is based upon the Debye diffraction theory, which is really quite different from the Bragg diffraction theory. In the Debye theory, each atom-atom pair scatters coherently within itself, but is incoherent to all other atom-atom pairs within a structure. And to calculate the diffraction pattern, you essentially go through every atom-atom pair in the structure and calculate the coherent diffraction from each of these atom-atom pairs, and then add them all together. So PDF is additive. You can look at individual atoms, individual atom pair relationships, and you can get down into the real nitty-gritty. What's going on locally? How are atoms moving about? Where is the lithium actually within this structure? So this is what I consider to be a much more realistic model of complex materials, but it is a complex representation. And what I want to talk about today is how we get to that representation and what it can tell us is going on inside the battery material themselves during aging, during cycling. What on earth is going on at the atomistic level? Now, again, it's been pointed out to me from my colleagues that radial distribution functions, paired distribution functions is probably a mystery to most of you, even if you have a strong crystallography background. So I put a few schematic diagrams together to sort of illustrate where it comes from. So in this first one, I have some rigid atoms arranged in a single lattice, if you like, a single layer. And if we start with the atom on the left, and we look at the separation or distances to all the other atoms within that particular lattice, then we can plot that out in a number of ways. We can plot it out as electron density, or occupation number, or probability of finding another atom. But essentially, when you do that, what you'll find is as a function of distance on the x-axis, every so often you'll have a well-defined peak where the nearest neighbor, next nearest neighbor, next nearest neighbor, etc., occurs within that particular structure or lattice. And so this could represent a very ordered material, well-defined atomic positions in a very reproducible lattice. In actual fact, what I've just described here is called the radial distribution function, but that is a close cousin to the pairwise distribution function. You can get from one to the other very easily. And if you think of these sorts of concepts, it will really help you understand what we're doing in the PDF and what we're reporting as terms of parameters to track battery performance. So let's go a bit further and introduce some disorder into this. So if you look at these little arrows on the top, I'm allowing random uncorrelated motion of these individual atoms. So this is point degrees of freedom. They could be vibrating, it could be temperature, it could be a point defect, for example. But this is point motion fixed to one particular atom itself. And if we go through our RDF or PDF again, what we now find is that this atom moves around a little bit. So it doesn't have a well-defined position where it occurs anymore. It has a range of positions. And normally we describe that by like a normal function, as I've shown here, a Gaussian function. And we have a parameter sigma, which is the sigma of a normal function, which is related to the half width. So you might say that this atom now has the ability to move around plus or minus sigma about its defined position. And we will be reporting the sigma number from the PDF calculations to give you some idea of how the lithium is moving about within the lattice. But that's not all what goes on when things disorder. That's point functions, point defects, but we have extended defects or extended functions like phonons, like acoustic phonons, for example. You can think of it like a Newton's cradle, where the atoms are all swinging around together, or if you join them by springs, it would probably be a better model. And this is for correlated motion between multiple atoms. So in this case, all the arrows are pointing in the same direction, and they gradually get bigger as you go along. And when we look at how that affects the PDF peaks, then you'll see that the peak broadening or the sigma value increases as a function of distance. And we characterize that by something called rate. So this is the rate of the increase in sigma, how do the peaks broaden as we go further out in distance. Now, if rate is 0, that's considered to be a highly ordered crystalline material. And if the rate goes to 1, then that's complete disorder. There's no structure there whatsoever. And so the numbers we're looking for in the rate will lie somewhere between 0 and 1. Closer to 0, more crystalline. Closer to 1, essentially total disorder. And the final concept is that of occupation number, as I mentioned before. Now, for this cathode material to work, the lithium has to move out from the lattice, has to move out through the layers. And as it does that, assuming this is lithium, for example, then the occupation of certain sites will go away eventually. Ultimately, they'll all go away. And as we do our radial distribution function, we notice that certain peaks are now going to be missing completely. They're just not going to be there. Actually, when you do the PDF, you have to look at these distances from every atom in the structure. And when you do that, you get peaks at all positions, in fact, but the overall intensity will be reduced. So as the occupation number goes down, the PDF peaks reduce. As the occupation number goes up, the PDF peaks increase. So the change in magnitude of the peaks, or certainly a family of peaks, allows us to isolate occupation numbers. So at this point, we've reached polling question number 1, where we can take a break and exercise our brains.
I guess, Simon, you can take a break, right? When we ask the audience a question. So we have a couple questions for you today. And the first one is, are you actively involved in novel battery design and manufacturing? So answers are coming in fast. I'm going to give you a few more seconds to just think about it. Am I involved in battery design and manufacturing? Okay, there are people who said not sure, actually.
Oh, interesting.
I guess that depends on the definition of
I guess it
novel
does.
battery.
Yeah. Oh, I see. Yeah, fair enough.
Okay, so I'm gonna close the polling in 3, 2, 1. Okay, let's take a look at the results. Actually, a lot of people said no, and 25% of you said yes.
Well, that's surprising. Yeah, interesting.
Maybe you're
PDF's an
interested in
interesting
PDF?
subject,
Yeah.
Yeah, it's probably PDF. It'd be interesting what other people are doing now. Okay, with that, I'll move on to the next slide.
Oh,
Actually,
so we've had
Gonna
one
take some
question come in
questions.
so
Oh, yeah,
far.
I'm
Simon.
sorry.
So let's
sorry, yeah.
so the first question that came in was, back on slides, I think it was like 10, 11, and 12 there. You mentioned BVS. Can you explain what that is? Is there some process to defining that?
Yeah, sure. So bond valence calculations, as you can see on the bottom left-hand corner, allow us to look at like novel battery materials. So as you're designing new materials, you start to get the structure. So the average structure, so the crystallography structure. We can then predict how free the lithium is to move through that structure, or how effective it will be as a cathode material, in fact, or as a solid electrolyte. You need to get mobility of lithium through that structure. So you're going to need to have layers or channels or pipes or something. And the BVS calculation allows us to do that given a crystal structure. And essentially it's based on the valence state. So it's cobalt 3 plus, lithium 1 plus, and oxygen 2 minus. So it takes in that ionic valence state and the ionic radius. And then based upon those two, it looks at all the positions where the energetics can be satisfied to satisfy valence and can satisfy the ionic radius. And based upon that, it finds a free pathway where the lithium can move through. So lithium can actually sit in many positions and still satisfy all the valence and bonding relationships, which is really quite interesting.
Okay, so yeah, so a quick follow-up is, so those channels, right? So they're asking, why are those channels important, right? And so it has to be the size, like the freedom of movement, right? It's how easily lithium can move through those channels.
Absolutely, and that is the critical design parameter, is how wide are the channels and can lithium freely move through those channels. I'm not sure that there is a maximum limit to that. But one of the issues, particularly with NMC, which is one of its main failure mechanisms, is as all the lithium leaves, right, you've got an empty channel. There's nothing there. I think it was Aristotle said, nature abhors a vacuum. So if you empty the channel, something bad's going to happen, clearly. And what normally happens is they collapse. And then when they collapse, you can't get the lithium back up through them again because there's no channel there. In fact, that's a precursor to, they call it the rock salt transformation for NMC, which kills the battery completely. So the channel width is critical, and we need to make sure it doesn't collapse. That's the main thing. It shouldn't collapse, and so it shouldn't nucleate, or is that the right word? Yeah, nucleate this transition to the rock salt structure, which will kill the battery completely. So yes, very important. And I think that I have indicated in the PDFs to follow that we can directly determine that distance from the PDF with no complicated analysis at all. Very easy. So that most important parameter we can get out very fast and very quick.
Okay. All right. That's good for now. Thank you, Simon.
Okay, we're good?
Yep.
So pair distribution function analysis. Let's have a look at this in a little bit more detail on our example battery material, which is the lithium cobalt 3 oxide. That's our archetype we're using, our analog, because it's a very, very simple analog for NMC. So assuming that you will eventually be going off and measuring your PDF, there are a lot of considerations in terms of how do you collect the data. And I think Keisuke, one of my colleagues, covered some of this before, but it's very important to think again about how you're going to collect data for PDF. The first thing is that PDF is total diffraction. You must collect at least as close as possible to the total diffraction signature from the sample. That's very, very important. And what does that mean? That means, number one, you measure the high Q, and you go, what on earth is high Q? Well, we'll look at Q a bit later on what it actually is, but it's inversely related to wavelength. So it means shorter wavelengths are better for total diffraction. And it also, you need to measure the high 2 theta. So you need to measure the highest 2 theta possible, 150, 160 degrees, and you need to go to shorter and shorter wavelengths, ideally. But of course, there's a balance there, and we'll look at different wavelengths as we go through that. So number one, total diffraction. Number two, isotropic. The Debye theory, unlike the Bragg theory, the Debye theory is isotropic, so everything is rings. In Bragg diffraction theory, everything is anisotropic. You get peaks in directions. So they're completely different in terms of the way they scatter, or way the models are built up, sorry. So you have to measure isotropic data. And so if you're using a single crystal, you have to spin it through all orientation. So if you've got a single crystal on a pin, then you've got to rotate the pin around and then move the crystals around like that. And that used to be called a Gandolfi measurement in the past. And secondly, thirdly, minimize sample corrections. In the bad old days, PDF was really difficult to calculate because there are so many corrections to get from measured data to instrument-free data, which is what you need for a PDF. Nowadays, we've made life really easy for you. With the Ragaku SmartLab Studio 2 program, I can calculate these very quickly. It's completely automated, and it'll do it for multiple instrument configurations. So it's a very powerful package. But to minimize sample corrections, the main ones I worry about are multiple scattering, multiple diffraction, and absorption. And that's minimized by having the simplest possible sample. So if you have a little grain, a little round grain, that's perfect on a pin. That's the perfect representation. But then you get low intensity. If you have a powder, then powder in a spinning capillary transmission is the next best. Most other geometries you can use, but it gets more complex. High Q, we've mentioned high Q before, not IQ, but high Q, very, very important, not only for total diffraction, but also for achieving the asymptote for the PDF. That will all be meaningless to you now. Hopefully at the end, you'll understand what I mean by achieving the asymptote for a PDF. But another consideration for high Q is that there's, because the signal level is very low, diffraction signal is very low because of atomic form factors, you have a lot of noise there. The noise is incredibly high, Poisson statistic noise. So you have to get a lot of intensity and count for a long time. And my recommendation on a measurement program is you measure very fast at low Q. So at low 230, you measure fast. And as you get up higher in 230, you slow it down and you collect data much more slowly at high 2 theta. And that's to minimize the noise. And you also need to check that you're doing it correctly. And for inorganics, the main thing is to compare to nickel. So nickel structure is completely isotropic, well known, and the results have been widely published. And this is the main go-to for calibrating PDF measurements. And these are some of the instrumentation that we use. A lot of the data will be measured on a 9 kilowatt SmartLab, horizontal transmission with a capillary stage. And some of it will be done on a micro diffractometer, a Synergy S, which in actual fact is a single crystal machine, using micro diffraction. And this is really to show that the way we calculate the PDF now is so robust, it's independent of instrument configurations that we're using. And we'll use 2 wavelengths. We'll use silver and molybdenum. And this is an example of a single grain of material on the end of a loop here, not a pin. But To me, I like this configuration, but then you need a micro diffractometer to collect the data. If you have a powder machine, then powder and a capillary is probably the way to go. Let's move on to measured data. This is collected on 9 kilowatt smart lab capillary. This was collected by my colleagues in Japan with silver radiation. And this is on our archetypal material, lithium cobalt 3 oxide. So this is what the total diffraction pattern looks like out to high Q. You get the dip in the middle here. That's not due to the instrument. That's a polarization issue because we use unpolarized X-rays. Once I have that data, the first thing I like to do with any active battery material is make sure it's the right material. So many times you buy some cathode material or you synthesize it and it's just not the right stuff. So the first thing I do with this is I pass it through a search match against the ICDD PDF 5+ battery database. Very useful to have, has almost all the current relevant battery materials. And I can identify that immediately as lithium cobalt 3 oxide. And this picture is just to remind me about total diffraction. If you're using an area detector, which is recommended for PDF, then you integrate around all the Debye rings, all these Debye share rings, to make sure that you are indeed getting a total diffraction pattern. So we have Q, it popped up there. So now you can see what Q is. This is 4 pi sine theta over lambda, and lambda is the X-ray wavelength, and theta is half of 2 theta, which is the diffraction angle. So what I'm showing in this series of images here is how we go through and calculate the PDF. This is all done automatically in SmartLab Studio 2, but I've taken snapshots on the way through, and the software displays all of these so you can stop at any point and check to see what's going on. So we start off with the measured data in the top left in red, although it's hard to see the full data, it's in red. And you also need a measured background or blank sample. Whenever you're doing total diffraction, you must have a blank sample data set. It goes through an automatic background subtraction based on the transmission X-rays through the blank sample and through the real sample, and gives you background subtracted data. This is then passed on to be normalized into electron units. So we start off with counts, we go to electron units, and that's done by normalizing and taking into account the Compton scattering, and we normalize to what's called the sum over F squared, which is the sum over all the atomic form factors, so the formula unit that defines the material itself. And why do we measure to high Q? We measure to high Q so we can hit the asymptote. This is the asymptote. It means that the sum over F squared is asymptotic or has the same high Q performance as you get from the measured data. Now, if you measure with copper you can measure to about 7, 8 in Q somewhere here. So if you chop the data off at this point, there's no way you can achieve the asymptote. So doing automatic PDF calculation is troublesome at best. So from there, we transform it to what's called the reduced structure factor. And it's very easy. We just subtract out the sum over F squared and then divide through by the sum over F squared. And we get the reduced structure factor, S of Q, although this is actually S of Q minus 1, I've plotted here, but essentially it's the reduced structure factor. And this is the instrument-free data. So all of the instrumental fingerprints that were present in the measured data have now been removed, which is why that calculation is so complex. And from there, we go through a windowed Fourier transform to make the PDF or G of R. And this is working through exactly with that lithium cobalt 3 oxide data. These are exactly the steps that it goes through, and these are exactly the plots and graphics that SmartLab Studio 2 will give you as it works through the data. And again, completely automated. Once you've got the data, once you've got the transmissivity and the material defined, then bang, it just goes straight through. So what can we do with this PDF data? So we've automated the whole process for you. We can give you a PDF now for pretty much any material on any of the instruments that we currently provide. What can you do with it? What information can you get out from it? Well, at the most basic level, without any modeling, of course, you can get the peak position. Exactly the same as you can do with a powder diffraction measurement. You can identify peak positions, and now in the PDF, these are in terms of distance, angstroms, and these are related to particular atom-atom pairs within the material itself. Now, we already discussed that this channel width is a critical parameter. We need to keep track of that, obviously. And one of the things that we can directly see in the PDF is this cobalt-cobalt distance. Now, cobalt has a lot of electrons. Same applies when it's NMC. Nickel has a ton of electrons in there. So any nickel-nickel, cobalt-cobalt relationships are going to have the largest peaks on the PDF itself. So all of these large peaks, these three I'm pointing out, these are related to cobalt. This is oxygen cobalt, this is cobalt cobalt, and this is also cobalt cobalt, but this is the channel width itself. So this peak, just straight from the PDF, just looking at that peak, will tell you what the channel width is and how the channel width is behaving, with no further analysis. So this is much like powder diffraction. You do a peak search, you can compare it against some known reference patterns. The same here, we have a PDF, we can do a peak search, we can find distinct bonds that we're looking for, and we can get that answer immediately, very fast. If we want to go beyond that, and most people want to go beyond that, then you have to have an atomistic model. So there's no getting away from that. If you want to do more complex analysis of PDF, then you must have atomistic models. And we typically have two sorts of atomistic models. We have small box models and big box models. Before I go into what these are, let's look at what type of data can we analyze with these models. Well, we can analyze the reduced structure factor, S of Q. In actual fact, that is my preferred approach. So although the topic here is PDF, I actually prefer to stop before I get to the PDF and analyze S of Q, the reduced structure factor. And you can do that with small box or big box models. Or you can go all the way to the PDF where you can do your peak searching and looking for atom-atom positions. And you can do the same atomistic model on the PDF itself. Now let's have a look at small box and big box. In the small box model, you have it, for example, a unit cell if it's crystalline material. If it's amorphous, you would have like a molecule or a molecular unit as your small box molecule. If it's crystalline, you have the unit cell, and into the unit cell, you can put some atoms. So this is the small box model, and these atoms can be moved around with or without symmetry constraints, depending on how you set the model up. And my recommendation for that is a third-party program called PDF GUI. It's an amazing program put together by Simon Billingsley's group. I highly recommend that. So if you're going to do PDF, you're working with crystalline materials, this is where you need to be step one, small box model. If you're a crystallographer, it's very easy to use, very intuitive, and I like it very much. In big box models, we're implementing our own big box model in SmartLab Studio 2, and that will be released in version 5. So keep a lookout for version 5, SmartLab Studio 2 for that. And in a big box model, we literally throw in thousands of atoms. So this one here has something like 7,000 atoms in a big box. And then we randomly refine those using what's called reverse Monte Carlo. So it uses specific statistic vibrations, and we can impose some bond constraints and atomic distance constraints as well. And then from our big box model, we can then calculate the PDF directly, or we can calculate the reduced structure factor. The same from the small box, although in PDF GUI right now, you can only do it against the PDF, so you must have a PDF for PDF GUI. You can't do it from SFQ. So let's quickly go through and look at some results. So this is of our lithium cobalt 3 oxide, again, our simplistic model. This is a fit to the PDF using PDF GUI. In my mind, that looks pretty amazing. But the R factor is about 16%. That is sort of typical for PDF GUI. I think for nickel, you can go down to like 8% or maybe a little less. But we're going out to 40 angstroms here. So we're looking at every atom-atom distance in a sphere of 40 angstroms, which is a ton of atoms. And so it's pretty amazing that we can achieve a fit as good as it is. And this is the little box model of that. And we can now start to extract out some of these parameters of interest. We talked about sigma. That's how much an atom can move around its position. It's about 0.1 angstroms for lithium. We'll come back to lithium occupation numbers here, but it's actually slightly low. So some lithium has already drifted out of the lattice in this particular case. Sigma for cobalt is much smaller. And this value is actually sort of typical for metals, maybe a little bigger, but it shows us that, that the metal framework is pretty rigid. not really any issues with that. Now we can go on to the big box model. And in this case, I've modeled it against S of Q. I get a much better fit to the data, 8.6% in terms of R factor. But don't forget, I've got like 7,000 atoms in that model I'm moving around, which is much less than what we have to play with in PDF GUI in terms of degrees of freedom. Nevertheless, it fits good. I'm just quickly extracting out lithium distances is 2.819 angstroms. We look at PDF GUI, lithium distances bang on, the same. Sigma for lithium, again, is bang on the same. They give us identical results. Big box, small box, PDF, or G of R or S of Q, we end up in the same place. So this illustrates the reproducibility of the technique. Now, I'm going to put these tables in for each individual material that we look at, and at the end, we'll put them all together so you can look at the variation between techniques and materials. But one thing to add is what we can do with the big box model is, because we have like 7,000 atoms packed in there, I can actually go out and generate maps of all the lithium relationships, cobalt relationships, cobalt oxide relationships, and I can plot those as a function of distance. This is done automatically in SmartLab Studio 2, which saves you a lot of work. And if we look at cobalt, first of all, this is how the cobalt distances are related to each other for this well-defined metallic lattice. And you can see these peaks are pretty well defined. If you look at the peak width variation, they don't vary too much. But if you remember from that introductory schematics, this tells us there's not a lot of disorder in the cobalt. It's pretty rigid, pretty well-defined positions. And if you look at the cobalt sigmas, this is the point variation. So if I take this dotted line and I take this back to 0, that's sigma. And the slope, again, the disorder rate is very, very, very low. So this is a quite ordered cobalt lattice, not much disorder in at all. If we look at lithium relationships, we can see straight away the peaks are way broader. And worse than that, the peaks increase in width as a function of distance. So the lithium is significantly more disordered. The point variation is almost an order of magnitude higher, but a little bit higher. But the disorder rate is tending towards an order of magnitude higher. So as you go from one lithium to the next, the rate they disorder is really quite dramatic. And eventually, about 20 angstroms, lithium is almost a C, which goes to support the BVS calculations that although lithium does have some positions it likes to be in, overall, as you go further out, it actually has a lot of degrees of freedom. And I went back and I put in the gap, the spacing between the cobalt layers, which we can track directly. Once we have it in this form, I can tell you it's 4.92 angstrom. So we can track that change in that spacing really, really quite precisely. We're now at polling question number 2.
So the second question, let me open this first. We had for the audience is, have you used the PDF before for materials characterization? Have you done PDF measurements and data analysis before? The answers are coming in. I think about a half of you answered the question. I hope everybody's still awake.
Oh, thanks for that.
She woke a couple of people up. We had a couple more come in after that.
There you go. Now they're waking up. So I'm going to give you a few more seconds. Okay, so I'm closing the polling in 3, 2, 1. Okay, let's take a look at the results.
Yeah. So it's majority of people, not using PDF.
And actually, there are quite a few people who have used it. A third of them. Mm-hmm.
Yeah, that's great. That's great.
Yeah, certainly in the bad old days, it was tough, PDF. But I think we've automated it now. So now there's no excuse, guys. You need to be doing this.
Yeah, that's certainly true.
Yeah. All right. So Simon, we've had a couple of questions come in. Actually, we've had a bunch of questions come in, but I'll just address a couple of them here really quick.
Okay.
So at the beginning of, let's say, this section, you were talking about line and point source. capillary pin mount, is do you see, you know, there's trade-offs on both of them, right? Is
Yep.
intensity for, you know, a single crystal versus you know, versus the powder, but the single crystal is more representative. Any advantage to either instrument, or aside from Ragaku saying buy both because we sell both?
Right.
Do you see any particular instrument kind of being the go-to?
Yeah, in my mind, there are two choices which I prefer. One is a micro diffraction system like the Synergy S single crystal system.
Mm-hmm.
And the reason there is you can use small particles, small fragments, and so the corrections that you need to apply are minimal. Plus, the data collection software, Crystallis Pro, for the Synergy systems, corrects everything to total diffraction and isotropic diffraction. So it's a very simple, straight-through, powerful way to do it. The other go-to is transmission capillary on a powder machine. When you've got lots of material, that gives you more intensity. And you go into high Q, you need lots and lots of intensity. So that's the big advantage there. If you're struggling for intensity, certainly for organics and things like that, a powder and a capillary is typically the best way to go.
Okay. The next question, I think this is a database. So Jennifer is asking, is there is a database of bonds within the Smart Lab software to determine the bonds, or do you have to know what elements are in the material before you search for the bonds? So I think she's kind of going from the right search match to bonds, right? And so
So Smart Lab Studio 2 will let you know where the peaks are in the PDF. But to identify them as cobalt, oxygen, or something like that, it needs a model. You're right. So you have to have a model in there. And we have a materials database that we build up with a lot of different materials. And so I previously built in lithium cobalt 3 oxide as a model in that database. So it already had that, yes. And we do have a small database, but you're probably going to have to add your materials into that database. Now, for organics, the bond distances are very well defined. So for organics, it's different. But for inorganics, you're going to need some sort of model.
Okay. Jennifer, if that doesn't answer your question, if I didn't frame it right, go ahead and submit another one and tell me what we missed. And then we'll take one more question, then we'll move on and we can answer some of the rest of these towards the end. So Mitchell is asking, can this analysis apply to amorphous materials?
Absolutely. That's where it started off. That's why I used it for like 20 years. We're going looking at amorphous and glassy materials. I'd say it's very powerful for that. The big box, small box models is currently defined, mainly aimed at, first of all, inorganics and crystalline, but there are equivalent models for amorphous as well.
Okay. All right. We've got a few more questions. We'll bring those up towards the end. Simon, let's make sure we get to finish your presentation.
Yeah, I am definitely running out of time. I've been dawdling. Let's undawdle. We're going to look at NMC. And I noticed a question came in about 811-622. No, I only looked at 523. That's the only one I studied this time. This is really just to illustrate the technique. What we're actually doing is we're opening up a lab in the Bay Area where we're going to have these capabilities. And so we invite people to come along with their materials and have a look. So if you've got 811-622, reach out to us. We'll be more than happy to do a study for you. So here's measurements, again, done by my colleagues in Japan. Smart Lab powder capillary. Now we've got NCM 523. That one is in red. And the original material we're looking at is in blue. I'm going to have to speed up a little bit here, so I'm going to start to speak a little quicker. I'm sorry. So tell me to slow down if you want. It's hard to see what's going on at that scale, but if I look locally, you can see that the patterns are very similar, but in the red one, the peaks are all moving to the left-hand side. They're moving to lower angles, and this is the NMC. So as we go from cobalt to NMC, the lattice is expanding. Diffraction is reciprocal, so in real space, if it's getting bigger, in diffraction space, it's getting smaller. And so we know the lattice is expanding when we go to NMC or NCM, and that has an impact on the channel width. We're opening up the channel, is what we're doing. So we go through and we do a small box model again. Good fit to the data, same R factor as we had for the pure lithium cobalt 3 oxide. We look at the sigma values. For lithium, it's about the same. And for cobalt, it's now increasing. So I modeled this still as the so even though this is NCM, I modeled it as cobalt. And Clearly, we have NCM in there, so it's a random alloying. So it's going to be very confused for the cobalt in terms of the modeling, and it's going to try and have to work out how best to fit that. So now the disorder or uncertainty parameter is increased to take into account different ionic radii, because it's going to expand and contract depending on which ion is in there. So you're going to have some variability. The big box model, we've talked about that. R factor has decreased from 8 to 14. Again, it's due to the random occupancy of the alloying. Randomness is incredibly difficult to capture in a big box model. You really have to go to like multiple hundreds of these big boxes to fully capture randomness. And so that impacts the R factor a little bit. But again, we get our sigma values and we get lithium distance values. We can make our table. And we can see here, if we look at the lithium sigma, from our single crystal, small box, big box models, we're getting increased disordering and mobility in the lithium as we go to the NMC away from the straight cobalt material. The lattice has expanded, it's considerably bigger. That would mean that the layers have opened up as well, which is a good thing. And the cobalt sigma has also increased. So we've got more disorder in the lattice, mainly because now it's a random alloy. If we look at the layer spacing between the individual metallic sheets, so now we're at about 5 angstroms. So it's increased about 0.1 angstrom going from cobalt to NMC. So we've opened that up. We've increased the mobility capability of the lithium. Now, again, this is part of the design considerations of new cathode materials. And PDF without any complex analysis can give you that straight away. As I make this material, what's happening now. Well, let's look at some material that's been cycled. Now, this analysis was done here in Houston, and the measurements were all done by my colleagues here in the lab, in the single crystal group, and in the business development and the XRD groups. And if we compare the measurements on the NCM starting material 523 with the cycled material, now this had only been cycled a short number of times, like 5 times. So this wasn't cycled down to the point where it had fully degraded and the battery had failed. Again, it's part of demonstrating of what's possible. It's not trying to solve the problem for you right now. We encourage you to bring your materials where we have cycle testing capability, and then we can really see what's going on for your materials, in fact. But the peaks are moving after cycling, and it's complicated. Some parts have expanded, some parts have contracted. So complex changes in the crystal structure from cycling. We go to our big box model, the small box model, and R factor is much the same, the fit is much the same, PDF-QE handles this, no problems at all. The sigma values, which surprised me a lot, are much the same. Certainly for lithium, the lithium degrees of freedom are really not that much different after cycling. Cobalt's getting a little bit more disorder, which we might expect. We go to our big box model. The fit is slightly worse, but not that dramatically worse. But again, from the big box model, we're getting higher sigmas than we get from the small box model. And again, I think that's because we're looking at, realistically a much, much bigger box. And it gives you more physically realistic parameters from the big box. The small boxes still has some consymmetry constraints because it's still sort of an average model, because we then have to expand that out to make the complete lattice itself. And this one was measured on the synergy, so the micro diffractometer with with molybdenum radiation. And we can bring all the data together. You've seen these already. You really don't need me to go through it in a lot of detail. So I'd like to save some time for questions at the end. But much the same as I've already said, the lithium is slowly disordering, no dramatic changes, a lot of disorder as a function of distance. The main change is that cobalt is definitely now more disordered than it was in the original pristine starting material. So we are disordering more in the cobalt lattice layer. And we can now move on to the second set of measurements. These were done with a smart lab 9 kilowatt, also working with molybdenum radiation, just to show you we can do the analysis on different instruments, different configurations, different wavelengths. The software has been automated to handle all of that. And in the final table, we'll compare those factors together. So this is the data from the powder diffraction system, again, there's really no surprises here. This follows pretty much the same trend that we've been seeing all the way through. And if we look at the combined data set, this is where we can start to look for trends. So one of the first things is if we look at the R factor, which is the ability of our atomistic model to describe the data, it gets progressively worse. So our simple models, they work well with lithium cobalt 3 oxide, but as we get to the random alloying and as we go through cycling, the system becomes a lot more complex, more difficult to describe. We notice that the cobalt sigma, so our metal layers are becoming increasingly disordered, particularly after cycling. And this is, remember, it's only like 5 cycles. So we're seeing disordering in the metallic layer. And we'll come back to that a little bit later. If we look at the lithium mobilities, slight increase, barely noticeable, really, a small increase in lithium degrees of freedom and randomness. Again, very little change in the disorder rate itself, which surprised me a lot. I expected to see tremendous issues with that. But where we really see a big significant difference is in the lithium occupation number. For the lithium cobalt 3 oxide, we had low occupation of lithium, which means that it was somewhat discharged. Some lithium had left. And so the pristine starting material is about 1. That's what we might expect. But even after a short number of cycles, we've got this increase in lithium occupation. So what on earth does that mean? You know, this is a crystal, right? So how can we pack more lithium into a crystal? It's got very preferred positions. That should not be possible at all. And this comes back to everything we were discussing before with layer collapse and rock salt phase transformation. Well, that was what we suspected was going on. So, you're going to have to wait. you're going to miss the hot punchline right at the end.
What a tease.
Don't leave early. Don't leave early.
Don't leave early. You're going to miss the best bit.
Okay, so this is the last question we have for the audience. So after, seeing all the examples and applications in the Simon presented, do you think that PDF analysis could be a useful characterization tool for your research? This is where you get rated, Simon. I think you're doing well.
The answers look like Simon's done a pretty good job here.
Yeah.
There's too many not sures there, I'm obviously not doing that well.
You don't like the not sures?
No. That worries me a lot. You'll have to tell me why you're not sure. I mean, guys, it's automated. Just press a button and it does it for you. So it's
now he's really selling it.
Yeah.
Okay, so about a half of you answered. I'm going to give you a few more seconds. Let me close the polling in 3, 2, 1. And let's share the results. 77% said yes.
Well, there you go. I'll take that as a silver star. How about that?
I think that is good, Simon. I think that is good.
And I guess, Simon, you can reach out to those people who said not sure.
I would like to know. Please reach out to me. Yeah.
He's saying we got lots of questions, but I want you to finish. So we'll take a couple at the very end, but let's get you finished, okay?
Oh, you want me to? Okay, I'll try.
Yeah, why don't you go ahead and continue? I'll make sure you finish before our 3 o'clock.
Yeah, I'm just took a look at some of the questions. Interesting. Okay, whoops, wrong button. So we wanted to look at what was going on in terms of the lithium layer. What on earth was happening? How can we get higher occupation of lithium? And we have a new toy, electron diffraction system, a Synergy ED, and that allows us to look at nanometer-sized particles and get crystal structures. Well, assuming they're crystalline, of course. But so what we can do is we can take the cathode material and we can scrape it a little bit off the aluminum collector, and then we can scan through the grains of the cathode material and get crystal structures. And this is how that's done. I mean, we have a TEM-like imaging mode, and then we can search across the TEM grid where we put a lot of particulates, and we can try and identify likely particles to study. That particular particle is about 200 nanometers or so. A lot of the particles have agglomerated together because I've just scraped the cathode material off the collector, so some of it's still stuck together. But they're all pretty much nanoparticles, so you can find hundreds of these things to study. We do a quick diffraction measurement, And you can see little spots here, and they're single spots, not rings or doublets. So this is a pretty good single crystal. Then we can go and collect a complete data set by rocking the sample, and we get a beautiful diffraction pattern. The statistics on this are truly incredible. I was surprised how well we can collect a diffraction pattern from a real cathode material after cycling. And it's really quite incredible. And one thing we noticed when we scanned across the particles is there are multiple polymorphs. So already we're beginning to see this degradation towards some rock salt structures. Particularly, we saw a lot of monoclinic structures coming out. So this is again indicative of the failure in the cathode material. And this is the crystal structure that we solved. Well, I didn't solve it. One of my colleagues, Lee, solved it in the single crystal group. And it's really fascinating. It truly is. So the metallic layers are really well defined. And now you can begin to see the hexagonal structure within those layers. Oxygen, no problems with the oxygen, pretty well behaved. But the lithium layer, oh my Lord, it's bad things are going on in the lithium layer. The lithium are the light blue spots, but all of this gold stuff is additional content that's moved into that layer. And what we believe is going on again is that components from the metal layer, so either the nickel, manganese, or cobalt, are popping down into the lithium layer. So as we drain the lithium out, the layer opens up, and so it can do two things. It can either collapse or something else will jump into that layer to fill the holes. And we believe this extra electron density is things dropping down. And I did a quick back of the envelope calculation, and if nickel is the thing that's dropping down, then it's about 4% of the nickel has dropped down into that layer. This is what's called is nucleation, the rock salt form, and is the death of the battery. So very quickly, we've discussed cathode materials, NMC in particular. We've looked at total diffraction and Bragg diffraction, and we've looked at big box and small box models and how they can be applied. And now we can move on to the final set Q&A.
Okay, so Simon, since we're running short, there's one question here that I wanted to ask. Actually, that your Synergy ED system there, that data made this I think this is a very relevant question. So can this be used to get relevant concentration of certain species? So for example, could I calculate the relative amounts of silicon compared to silicon oxygen or silicon nitrogen in a silicon anode material? And I'm wondering, I was thinking about that, the diffraction, the single crystal pattern seems like it might be.
It could be. First of all, we have to ascertain whether the anode is amorphous or crystalline. If it's crystalline, then we have the Synergy ED, the electron diffraction can certainly do that. And a PDF can do that as well very easily, with some sort of starting atomistic model. Now, if it's amorphous, providing you have a model of the material, then we should be able to do that as well. But the challenge with amorphous materials is coming up with that starting model. How are you going to build that out atomistically to do the calculation? So assuming it's amorphous, I'd suggest a small box model where you build certain structures from silicon oxygen, silicon nitrogen, and then you see where they appear within the PDF. Or if that bond distance is well defined, for example, so I guess silicon, I guess all of these bond distances are very well defined. So you could look in the PDF for those bonds. Are they there? And you could do it that way, in fact, as well, just very simply. No model at all.
Okay. All right. So, hey, we got a bunch of questions. I think Simon will just have to come back to these after the session.
We're saving all those questions, so Simon will get back to you.
Yep, I will do. Well, thank you all. So I'll follow up with your questions.
And we have this recorded, and we'll put it on our website, hopefully tomorrow, if not on Friday. And please don't forget to register for the next workshop. I put the link in the chat. And the next webinar is about elemental analysis of battery materials. Please join us next time is in June 19th. And we hope to see you there. Thank you for joining us.
Yeah, thank you all. Much appreciated.
Bye-bye.
Bye for now.
Bye.